Hello, this is our Lab 3 demo. Our lab members are Yujia, Haran, and Taoha, and we will be introducing a decoder that can both perform ALU operations and a finite state machine operation. And let me show you how we can do that. So previously, we know that from Lab 2, a decoder can take in two inputs, A and B, a 4-bit instruction, a control bit, and a carry-in bit, in order to calculate either the arithmetic or logic result of your Boolean expressions. I was also, however, I don't want to allocate 14 ports on my board to taking all of this information because that's just too much. So I thought about adding a sequential logic component so that now I only have to push one button, which is data in. As long as reset and clock is set to 1, every time I push the button, one bit, either 0 or 1, will be recorded into the variable called store. So technically, our program has quote-unquote memory. And I also have a counter over here to count how many times I have pushed the button. So if counter is greater than 14, which means I have already sent in 14 bits to the store variable, that means I can just start assigning every bit to the actual variables that I want to play around with. So the first 8 bits of the stored variable are going to be used for inputs, next 4 for instruction, next one for control, and the last one for carry in. Looking at this clock sequential component, I thought it would be a good idea to incorporate what we learned in class right now, which is flip-flop design. So I actually just borrowed a idea from the textbook, which is problem 50 in chapter 5. So we wrote this program for homework 7, and I thought I want to try if I can implement it in real life. So over here, how are we gonna let the decoder also do the job of a FSM? So the trick is, if you look at the control bit, I'm sorry. You don't have to choose whether you want to you want to use ALU or finite state machine because they are computed at the same time. You have control over if you want to show the output of finite state machine or not. And this is governed by the output, which is 1 bit out. So previously, this output is just the carry out result of the ALU. But I thought about, because the output of finite state machine only requires one output as well, so I thought about using a if-else statement. If the control bit is 0, then we will display the carry out bit of the ALU calculation. But if it's 1, then we might as well just make it a finite state machine output so that while you are performing your arithmetic or logic operation, you can also calculate what is going to be the output as you push the button to send in some inputs to the finite state machine. That is the basic idea of this decoder. So in summary, 3 modifications: a sequential logic, a finite state machine, and the last one I forgot to mention is that in our ALU design, previously there was a operation which is A plus 1, but I thought that would be too easy. So I just modified that into a carry save adder, which is over here. So let's see if this program can work out. And you probably already see that when I push it to the board, the bit stream could not be generated for some reason, so we actually failed the implementation. But I want to show you that in simulation this technically can work. So if we look at the test bench for decoder lab 3, what I did was I set clock and reset to be 0 to begin with, and then 5 seconds later I set reset to be 1 so that I can start my recording. I also let the clock alternate between 0 and 1 so that it can sample the information as what a flip-flop design will do. So now now data in switch between 1 and 0, you can think of them as either 14 bits of information is sent to the ALU. You can also think of that as I am giving different inputs to the finite state machine. So as you can see here, the ALU is performing without problems, but for some reason because I chose my 1-bit out to display the output of finite state machine, for some reason it does not take on any value, and I spent a lot of time debugging that part, but we couldn't find what's the problem. So I guess that's one drawback of our design. We have to figure out what's going on. Thank you. Wrote the Verilog for VGA display, but it couldn't generate the correct output as we expected. I don't know what the issue is, because we tried to debug it for so many times, but there was no solution. But I want to show you that we actually wrote the program, and the ideas behind that are correct. I'm sorry we don't have a demo for this. Thanks.